In this work, we motivate the study of the curvature of loss with respect to the input data points. We show that it is useful to identify visual properties of datasets and can be utilized to create cosets of extremely small sizes that result in higher accuracy than other contemporary methods. We plot the histogram of many well-known architectures and show that there is an unexpected concentration of samples with very low curvatures, shown on the peak around 0. We show that there are samples that are common across these peaks in different architectures and across different seeds of the same architecture. We visualize these samples and show that there is a very clear trend across low curvature and high curvature samples. The low curvature samples shown on the left are clean images. They're quite often free of visual clutter and very prototypical of their labels with no confusing backgrounds. However, the high curvature samples are often occluded and sometimes of unidentifiable labels. We use this to create cosets of small sizes using low curvature prototypical samples and show that we outperform state-of-the-art methods significantly. To motivate this, we look at the loss curve with respect to the training epochs and see that the training loss keeps decreasing. However, after some point, the validation loss will increase. This is the optimal point where we want to stop training. Towards the left are the early epochs, we have underfitting, and in the later epochs, the model has been set to overfit. Let's look at what this looks like in the input space. We have two classes that we want to differentiate between, shown in green and purple. On the left, we have an overly simplistic model, and the model underfits to the dataset. That is, the decision boundary is just not complex enough to understand the nuances of the data distribution. However, when we have a super complex network, shown on the right, the decision boundary tries to memorize each and every data point and results in a highly complex, highly nonlinear boundary. If you look at these images for a second, we can identify a property that sets them apart, and that is the curvature of the decision boundary, or in other terms, the curvature of the loss with respect to the input data point. The curvature of the loss has been studied quite heavily, but with context to the weights, not with respect to the inputs. To measure this, we are going to look at the eigenvalues of the Hessian matrix. If you have a neural network with an input x that is d-dimensional and generates a loss, L, the Hessian matrix is the second derivative of the loss with respect to the input. It's going to be a d cross d-dimensional matrix where each element is the second differential of the loss with respect to the I and the j input points. However, calculating this is quite expensive, and doing the eigendecomposition of this is also quite expensive. And hence we're going to make some relaxations. The trace of H summarizes all eigenvalues because it's the sum of all eigenvalues. And we are going to look at the low complexity Hutchinson's trace estimator to estimate this efficiently. Hutchinson's trace estimator says the trace of H can be said to be the expectation over multiple random Rademacher variables of the quantity V transpose HV. V here is the Rademacher variable, which is just a d-dimensional vector with each element being +1 or -1 with equal probability. We do not care about the sign of lambda I, we rather care only about the magnitude, and hence we're going to look at the trace of H square, which is the sum of the square of the eigenvalues. We can show that this reduces to the Frobenius norm of the Hessian vector product averaged over multiple such random Rademacher variables. This is quite useful because this means that we do not need to calculate the entire Hessian, just the Hessian vector product, which can be efficiently calculated using the finite set approximation as shown. This means the trace of H square is proportional to the quantity shown on the right. We're going to make one final relaxation here. Instead of taking average over multiple random Rademacher variables, we are going to consider only the gradient direction, since that has been shown to be the direction of maximum change. This means this is a final form of curvature estimation, and we show what this looks like practically here. We have a neural network that gets an input x and generates a loss L of x. We then backward propagate it to get v, which is the gradient direction. We take the sign of this gradient direction, divide by the magnitude of it, and perturb the original input x in a small amount along this direction. We then forward propagate this to get the new loss, subtract the original loss, and back propagate this term to get the Hessian vector product. We take the Frobenius norm of this Hessian vector product, and that is our estimate of the curvature for this data point x. The cost of performing this is actually 2 extra backward passes per sample, but it can be parallelized for a batch, making it much faster. Let's look at what the results of calculating curvature across different architectures for CVPR is. First, we're going to train a ResNet 18 to convergence and calculate the curvature of the training samples at the very end of training. We then plot the histogram of the curvature of all 50,000 samples. Here's what it looks like for ResNet 18, and we see an unexpected concentration of samples with very low curvature. This trend repeats for many different architectures, such as AlexNet, ResNet 101, and VGG19. The first question that arises is, Are there common samples in this concentration around 0? And the answer is yes. To visualize this, we are going to plot cumulative curvature. And the reason we're plotting cumulative curvature is because only the samples that are very low curvature across multiple seeds or architectures are going to show up in the peak at 0 once we've accumulated them. And on the left, we are showing the results for accumulating over different seeds of ResNet 18, and on the right, we're showing the results for accumulating over different architectures. And as we can see from the purple curves, in both cases, we still have a concentration of 2,000 plus samples with very low curvature that are common across all the seeds or architectures. This commonality suggests that curvature is revealing data set properties rather than architecture or training setting dependent properties. We now visualize what these samples look like. On the left, we have the 10 lowest curvature samples per class, and on the right, we have the 10 highest curvature samples per class. And if you look at this image, we can clearly identify some emergent properties. The low curvature samples are clean images in the sense that they're free of visual clutter, they're quite prototypical of their label, and there are no occlusions. However, on the right, we have cluttered images that are quite unclear. This means that curvature is revealing interesting visual properties of the data sets as well. And this trend repeats for CIFAR 100 as well, where we have prototypical images of apples and pears on the left, whereas uncommon pairs such as something that looks like a potato on the right. This also repeats for ImageNet. We're going to now utilize this to create core sets. Core sets can be thought of as summarizing big data sets into smaller, more efficient subsets. And our proposed method to use curvature to create core sets is called slow curves. We're going to measure curvature as discussed earlier, and then we're going to sort the entire training set by curvature and choose the desired samples per class with the lowest curvature. We're going to create a new network that's going to be trained only on these samples from scratch, but training this new curvature is going to have an additional regularizer that penalizes the curvature. We are selecting low curvature points from a parent network, and we are going to make sure that the student network still has low curvature by penalizing this. Let's look at what happens when we create core sets of small sizes using our method. This is the result for ResNet 18 in CIFAR 10. And on the x-axis, we have different number of images per class, and we can see that we have small core sets. On the y-axis, we show the accuracy of the network. Our method is shown in blue, and we can see that in most cases, our method performs most of the other core set selection methods. We have random selection shown in orange in particular, and we can see that our method outperforms random sampling by 1 to 9%. We also wanted to see whether core sets identified from ResNet 18 would generalize to training on many different student architectures, and we see that in all cases, we still outperform random sampling by an average of 5.3%.